Hello dear students, welcome to my fourth class on Module 3 Relations and Functions. In this lecture video, I'll be discussing about two important theorems of functions, that is Theorem 1 and Theorem 2. So first is Theorem 1. Theorem 1 states that a function f from a to b is invertible if and only if f is 1 to 1 and on to. So in the first part, I'll be proving that by taking f is an invertible function, I'm going to prove f is a 1 to 1 function as well as onto function. So to prove f is a 1 to 1 function, we must have the condition that if f of a1 is equal to f of a2 for all a1, a2 belongs to the set A, then we must get a1 must be equal to a2, and to prove f is a onto function, we must have a pre-image in the non-empty set A here. This is first part. In the converse part, I'll be using f is a 1 to 1 function and onto function, and I'm going to prove that f is an invertible function. Proof. Suppose that f is an invertible function, so then obviously we'll be having one more function g which maps from b to a, such that g of f will be equal to ia and f of g will be equal to ib. Both are ia and ib are identity mappings, and I'll be taking two elements a1 and a2 from the non-empty set A. Then I'll be taking f of a1 is equal to f of a2. Okay. So now for this function f of a1 is equal to f of a2, I'm going to apply the g function on both the sides. So I'll be getting what? G of f of a1 is equal to g of f of a2. So now I'm going to apply the composite property. I'll be getting what? GO f of a1 is equal to GO f of a2. This is by using composite property. So I'll be getting what? This GO f is nothing but IA. This is because of f is invertible. So I can replace this GO f is equal to IA on both the sides. So I'll be getting IA of a1 and IA of a2. So again I'm telling, to simplify this part, I'm going to use the definition of composite function. So I got GO f of a1, GO f of a2, and this GO f is nothing but identity mapping because f is invertible. So I got IA of a1, IA of a2, and this IA of a1 always equal to a1 and IA of a2 will be equal to a2. So from f of a1 is equal to f of a2, I got IA1 is equal to a2. So this proves that f is a one-to-one function. So now I must prove f is a onto function. So to prove f is a onto function, I'll be taking an element b from the non-empty set B. So then g of b will be must be in the A, right? So if I choose b from the set A, from the set B, I'll be getting g of b from the set A. So then b will be equal to what? IB of b. So I can write b will be equal to IB of b. And since f is an invertible function, I can replace IB is equal to FOG of b, right? So it will be equal to FOG of b, and again by using the definition of composite function, I can expand this FOG will be equal to f of g of b. So now what I can conclude that this b is the image of the element of g of b which belongs to the A under f. Therefore f is an onto function as well, right? So now in the converse part, I'm going to consider f is a one-to-one function and onto function, and I'm going to prove that f is an invertible function. Okay. So since f is a one-to-one and onto, for each b belongs to the non-empty set B, there must be a pre-image in A also. So I'm choosing I'm choosing a unique element A from the set A such that b will be equal to f of A. So now I'm going to consider one more function g which maps from B to A, defines that g of b will be equal to A. So now I must prove f is an invertible. To prove f is an invertible, I must prove that GOF must be equal to IA, FOG must be equal to IB. So we'll see that. So I'm taking GOF is equal to A, of A will be equal to G of f of A. This is by using composite functions. So it will be equal to further G of B because f of A is equal to B, and this G of B will be equal to A. I can read that IA is equal to IA of A. So since I'm taking A from the non-empty set A. Similarly, f of g of b will be equal to f of g of b. It will be equal to f of a because g of b is equal to a, and f of a will be equal to b, and b can be written like ib of b. This is from the set B. So hence I can conclude like f is an invertible function, that is g is the inverse of f. Theorem number 2. If f from a to b and g from b to c are invertible function, then GOF from A to C also invertible function, and GOF inverse will be equal to F inverse of G inverse. So from this property I must prove GOF of inverse must be equal to F inverse of O G inverse. So now proof. So since f and g are invertible function, so they are both one to one as well as onto also, because f and g are invertible. This is because of previous theorem. So now if f and g are one to one and onto, obviously the composite GOF also an one to one as well as onto. So therefore GOF is an invertible function. So now I'm going to take the inverse of f. So I'm taking so let me consider f inverse is the inverse of f, and which maps from B to A, and the inverse G inverse from G, which maps from C to B. Okay, therefore I'll be taking H is equal to f inverse of G inverse. So then I can conclude like H is a function from C to A, which maps from C to A. So now I'm going to consider GOF of H. So to find GOF inverse value, I'm taking this condition now. GOF of H will be equal to what? So I'm replacing H is equal to F inverse of G inverse. So on simplifying this, I'll be getting what? GOF O F inverse of G inverse. It will be equal to GOIB of G inverse. So IB is nothing but FO F inverse. So on simplifying this, I'll be getting IC here. So same thing for HO GO of F. So it will be equal to what? It will be equal to F inverse of G inverse of GO of F. On simplifying this, I'll be getting what here? IA. So like what we can observe that here, GOF of H will be equal to identity mapping, and HO of GO of F will be equal to an identity mapping. I got it here. Therefore, H will be equal to what? GOF inverse. But in the starting I assumed that H will be equal to F inverse of G inverse. So I can conclude like GOF inverse will be equal to F inverse of G inverse. So this completes the proof of the given theorem. Thank you.